So welcome to the fifth lecture on quantum field theory. So remember that in the previous lecture, we wrote down the most general solution to the free classical Klein-Gordon equation, and it was given as a Fourier integral because we found that the plane waves are solutions to the free Klein-Gordon equation, and therefore the most general solution can be written as a sum over all the frequencies. And as we know, that's given by the Fourier integral. So this was the classical expression. But then what we did is we quantized our free real scalar field. And to do that, what we did is that we took the classical Fourier modes, AK and its complex conjugate, A star of K, and we replaced those by their operator counterparts, which again we write as A of K and A dagger of K. This was the first thing we did, and then what we said is that we imposed on A and A dagger a generalization of the commutation relationship that we impose on the creation and annihilation operators for the harmonic oscillator. So we wrote that the commutator of AK and A dagger of K prime is given up to some normalizations, which are important, but they are conventions. 2 pi to the cubed, 2 to the power omega k delta of k minus k prime. The delta function is the three-dimensional delta function. And we also assume that all the other commutators, such that the commutator between two A's and the commutator between two A daggers were 0. Now, several observations are in order. So let's make some observations. The first one is that these commutation relationships are equivalent to the commutation relationships between the scalar field and its canonically conjugate momentum, but at equal time. So these are equivalent to equal time canonical commutation relationships. And those were given by the field variable at some time t and its canonically conjugate momentum pi at some other, in general, some other spatial point x prime, but at the same time. That's given by I times the three-dimensional delta function x minus x prime. We also had that the equal time commutation relationship between phi and itself, as well as the equal time commutation relationship between pi and itself, vanish. Two set of commutation relationships, these ones and these ones, are equivalent and they are connected by Fourier transform. And the Fourier transform formulae was given in the last lecture. So since we impose quantization condition at a fixed time, we can ask, do these commutation relationships, how do they depend on time? Or do they actually, these operators, do they actually depend on time? Well, that's a very good question, because coming from classical physics to quantum mechanics or quantum field theory, we have to make a decision what picture we are in as far as these operators are involved. Now, since we chose these commutation relationships to be at a fixed time, which we can take, say, to be 0, we conclude that these commutation relationships, as well as these guys, are in the Schrödinger picture. So remember Schrödinger picture from quantum mechanics. In the Schrödinger picture, operators, which represent observables, in general, they do not depend on time. So these are, in general, independent of time, whereas the states, say psi, that would be dependent on time. So let's just use the bracket notation. And their time dependence is given by the Schrödinger equation, which is written like this. H is the Hamiltonian. Now, in this case, we are taking H bar to be 1. So this was the time dependence of the states. And if H is a time-independent Hamiltonian, this equation can be integrated to write the state psi at time t is given by the time evolution operator, which is e to the power minus I h t, acting on the state psi at time 0. So this is equivalent to the Schrödinger equation, and it's a solution to the Schrödinger equation. Now, in quantum field theory, especially when we're dealing with free quantum field theory, it is convenient to use instead the Heisenberg picture. So the Heisenberg picture is a view of quantum field theory where the states are taken to be frozen in time. Usually they're taken to be at time 0. And the Heisenberg operators, which are the observable, they are taken to be functions of time. And these operators are defined to be the time evolution operator conjugating the operator in the Schrödinger picture. So it'll be something like I, e to the power I h t times O. This is the Schrödinger picture operator, e to the power minus I h of t. So the justification for this formula comes from the fact that in quantum mechanics, and therefore also in quantum field theory, the basic observables that we deal with are inner products. So if you have an operator, then the inner product of the operator with some states is psi and phi, so which in the Dirac notation can be written as psi O phi. Now this is a time-dependent quantity, but the time dependence can either be in the operator or it can be in the state. And so we can write this guy as psi t time dependence O, which is not time dependence, phi of t. But we can write the state psi of t at psi at 0 time evolved. So I get, because it's the Hermitian conjugate, I get a plus sign here. And then I've got an O here. And then on the right side of O, I get minus I ht acting on phi of 0. And now this is nothing but the definition of the Heisenberg operator in the Heisenberg picture. So we get O of h, which is a function of t, and then phi of 0. So we see that these guys are the same both in the Schrödinger picture and the Heisenberg picture. Now, the Heisenberg operator O of h. Now, how does it evolve in time? Of course, we've just seen that its definition is given by e to the power I, h of t, O in the Schrodinger picture times e to the power minus h of t. Now, the Heisenberg equation of motion, which is the time derivative of O, so this is, suppose that the original Schrodinger picture operator O is independent of time. If that is the case, then the time derivative of O is going to give me d by dt acting on these three factors, e to the power iht, O times e to the power minus I, h of t. So if you use the Leibniz rule, what happens with this guy brings down a factor of I, h, and then I have everything else. So I do get O of h at t, and then the second term would be this thing acting on this, but this is time independent, so that won't contribute anything. And the last term would be this acting on this. And that is going to give me minus OH of t times I of h. Or in other words, we can write this as the time derivative of the Heisenberg operator is given by I times the commutator of the Hamiltonian and the Heisenberg operator. So this is the evolution equation in the Heisenberg picture. This is basically what replaces the Schrodinger equation in the Heisenberg picture. So now note that the Hamiltonian is kind of special because the Hamiltonian in the Heisenberg picture would be given by e to the power plus I h of t times h e to the power minus I h of t. But h will commute with h, and therefore, if you use the BCH formula, this thing just goes through here and this cancels this, and therefore we have h in the Heisenberg picture is the same as h in the Schrodinger picture. So this is kind of a special property of the Hamiltonian. So now let's take a little detour and ask, how do the creation and annihilation operator for the harmonic oscillator, behave in the Heisenberg picture? And that's because we saw that our Hamiltonian for the real scalar field was some generalization of the harmonic oscillator creation and annihilation operator. So for the harmonic oscillator, the Hamiltonian in the Schrodinger picture was A dagger A plus half times h bar omega. But of course, omega h bar is 1. So then the annihilation operator A of h is given by e to the power I of h of t times a e to the power minus I h of t. So to evaluate this, we use the BCH formula. And according to the BCH formula, we get a power series. The first term is just a. The second term would be I of t and the commutator of h and a. And then the third term would be I of t whole squared divided by factorial 2 and the commutator of h with another commutator, which is a commutator of h and a. So two nested commutators. And then the third term would be it cubed divided by factorial 3, three nested commutator of h's with 1a, and so on and so forth. But we know that the Hamiltonian, which is given by the number operator plus half times h bar omega, and therefore if I take the commutator of the Hamiltonian with a it just becomes the commutator of the number operator with A times h bar omega. And we know that this commutator is nothing but minus of A, so we multiply that h bar omega. Well, of course, we are taking A h bar to be 1, so which is minus A omega. So if I use this, then this power series can be very easily evaluated. So AH of t, the first term will be A, and then the second term would be, I will get a factor of minus 1 and a factor of A here. So I'll get, for the second term, plus minus I, the minus coming from the commutator T, but we do have a factorial 1 times A. And then the third term would be, so I will get from this commutator a minus A, and then from this commutator again we'll get a minus, we'll get another minus A. So we get two minuses and one A. So we can write that as minus I t squared divided by factorial of 2A. And then the third term would be minus I t cubed divided by factorial 3 times A. So we say that the A factors out, and then everything else just becomes the power series of e to the power minus I. Sorry. There's also the factor of omega, so there should be omega inside the bracket. Here there should be omega. There should be omega. So we get e to the power a e to the power minus I omega of t. So, but the a here is nothing but AH at time 0. We get e to the power minus I omega t. So in conclusion, the annihilation operator in the Heisenberg picture is given by the annihilation operator at time 0 times e to the power minus I omega t. And therefore, the Hermitian conjugate of that would be given by simply this formula. So now what we can do is that we can just use this and very easily generalize, what's going to happen in the quantum field theory case. So if I took the quantum field after I quantized it at time 0, then my quantum field phi at time t0 is going to be given by d of cubed of k over 2 pi cubed 2 of omega of k. And then we can, towards the end of this lecture, I will show that this omega k is nothing but the energy, but let's not jump ahead. And then we have a of k times e to the power plus I, the dot product between the three-dimensional k and the three-dimensional x, plus a dagger of k, e to the power minus I, and a three-dimensional dot product between k and x. But now, if I look at the Heisenberg picture generalization of this, then the field phi at some arbitrary time t is going to be given by e to the power I, h of t, and then phi of x at 0 time, e to the power minus I, h of t. But these are nothing but creation and annihilation operator. And here we have the time evolution operator and its conjugate. Therefore, it's just a very easy exercise to show that this will result in this thing evolving with a factor of this and this. Now what is this? This was nothing but the energy of the harmonic oscillator. So it was minus I e of t, and here it was a h dagger of 0 e to the power plus I e of t. So that's exactly what we would have here, and therefore inside the Fourier integral, we're going to get d cubed k 2 pi cubed 2 of omega k, and then here we get a of k, and then we get e to the power minus I et plus I k dot x, and then we have plus a dagger of k e to the power plus I et, and then we get minus I k dot x. So we see that these are nothing but four-dimensional dot products. So we can write phi of h at some time t is nothing but d cubed of k by 2 pi cubed 2 omega k a of k, three-dimensional, and which is of course also the Heisenberg operator at time t0, and then e to the power minus I, four-dimensional dot product kx, plus a dagger of h of k, and then e to the power plus I kx. So what we're going to do from now on is that because we're going to assume that we are in the Heisenberg picture, we're going to drop the subscript h. So we're going to write this as phi of x. X is a four-dimensional space-time coordinate, and then this will be d cubed of k divided by 2 pi cubed, and this should be, let's just put it e here because we know that's what it is, and then we get a to the power, a of k e to the power minus I kx plus a dagger of k e to the power plus I kx. And this is looks exactly like the expression that we derived for the Fourier series for the classical case. But in this case, this is a very important distinction that phi is an operator, a is an operator, a dagger is an operator. So the other thing we can do is that you can very easily show that starting from the Schrödinger picture commutation relationship, the Heisenberg picture commutation relationship would be a of h at say time k and at some time, at momentum k and time t, a of h k prime at the same time t is the same thing as the a of h at time 0, and so there's a dagger here, and ah dagger at time k0, but at momentum k prime, and that will be given by 2 pi cubed 2, say, e of k delta cubed k minus k prime. And we also have all the other operators such as a dagger, and a dagger. The commutators of those things will be 0. And also, similarly, you can put h here, but from now on, we are not going to put h. And so you can also show that, in the Heisenberg picture, the equal time commutation relationships also hold. These are very easy things to show because all you're doing is conjugating by the time evolution operator and its conjugate.